Good evening, everyone. Thanks for coming out on this kind of crummy night. My name is Roger Moore, and tonight is the real North Star. The title is, there's a little satire in that title. I mean, we're all somewhat familiar with the North Star, although when we ask people to locate it, they often have trouble finding it, or think that it's a brighter star than it actually is. So we'll talk about that. Our North Star is actually not a single star, it's a system of stars, and there's some unusual properties to it, so we'll go into that. And it's also the North Star that we have now has not always been the North Star and won't always be the North Star. So we'll talk about why that happens and implications that has for astronomy. So of course I'm talking about Polaris, which is in the constellation of Ursa Minor. This is a view, if we had a clear night and you went outside and looked north, this is what you'd see, minus the labels and lines. But the North Star is located at the end of the handle of the Little Dipper. Now, unfortunately, we can't see most of the stars of the Little Dipper, so we need a different way to find the North Star. But it's visible all night, on any clear night, from northern latitudes. So once again, this is what it would look like if you could go outside and look north right now. So the Big Dipper is handle down, probably be right over the school. And why is it called the North Star? Well, because Earth's north axis of rotation points almost right at Polaris. Not quite, but almost. The name is derived from Stella Polaris, the Latin, or pole star. And it's not one of the brightest stars. It's only about the 48th or the 50th, depending on who you ask. So this is a list of the 50 brightest stars, and there's several of these that are up tonight. Unfortunately, we won't be able to see them. Sirius, which is the brightest star in our night sky, is up right now. Pollux and Castor, which are both in Gemini, they're both up in the sky right now. And let's see, Rigel and Betelgeuse, both in Orion, they are both up in the sky right now too. Betelgeuse is a very interesting star. It's a red supergiant that they know will eventually end its life as a supernova. And it's a variable star. That is, it brightens and dims over regular periods of time. Not enough that the casual observer would notice. But in the last 2 or 3 months, Betelgeuse has dimmed significantly. It's dimmed much more than anybody has seen before, and they're still trying to figure out what that means, why that's happening. But you have to go all the way down here to the bottom right of this list to find Polaris. So it's not a particularly bright star. It's been used by sailors and explorers for centuries for navigation. And because it is at the north rotation axis, if you measure the angle to Polaris from the horizon, that also equals your latitude above the equator. So the further north you go, the higher Polaris gets in the sky, till you get to the North Pole and it's directly overhead. The further south you go, the lower it is until you get to the equator where it disappears. Unfortunately for the southern hemisphere, they don't have an equivalent star, a corresponding South Pole star. The closest they have is a much dimmer star that's farther away from the pole. So how do you find it? Well, everybody can recognize the Big Dipper, and all you need to do is find the end of the bowl. Starting inside the bowl and working your way out, you follow those 2 stars, and it'll point you right to the next brightest star, which is Polaris. The beauty of that system is that it doesn't matter which way the Big Dipper is facing. The same thing still works. Start at the bottom of the bowl, work your way out, and it'll point you right to Polaris. So once you know Polaris, then you know all 4 different directions. So it's easy to find it. And you can get a rough idea of your latitude, that is how far above the equator you are, simply by using your fist. An adult's fist held out at arm's length covers about 10 degrees of the sky. So you put the bottom of one fist on the horizon and you just stack them like this until you get to Polaris, which works out to be about 4 and change from our latitude. And that's about our latitude. It's about 41.5 degrees north. So we'll show you a little video. This is what you would see if you could stand and face north and watch the sky for 24 hours and ignoring sunrise and sunset, you'd see what happens. And while we do this little video, watch what happens to Polaris, which is right there, and watch what happens to the Big Dipper. So notice Polaris does not appear to move at all. And the Big Dipper never goes below the horizon, again from our latitude. And also because of this, anyone with a digital camera and a tripod can do cool things like this, where you just point your camera at Polaris, take a series of long exposures, this was 90-second exposures, and then stack them together in software, and you can see for yourself Earth rotation. So Polaris is about a 70 million year old triple star system. Polaris A is the main star, that's the one we see. Polaris B, which you can see in most small telescopes, was discovered by William Herschel in 1780. Going back to about 1930, they knew that Polaris A had a close companion because of the way it wobbled in the sky, but it wasn't until 2006 that the Hubble telescope actually imaged this closer companion, Polaris AB. So Polaris AB is only about 3 billion kilometers from Polaris A. Big numbers, but when the Earth and Pluto are on the same side of the Sun, they're about 3 billion kilometers apart. So the distance between those two stars is only the distance between us and Pluto. So it's not a remarkable star in our skies, but it is an enormous and very bright star. It's what's called a yellow supergiant star. It would be about 2,500 times brighter than our Sun and about 40 times wider. But it's far away. It's almost 480 light years away. It is also the closest Cepheid variable. Cepheid variables are stars that brighten and dim on a regular basis. And they are one type of star because of this relationship that was discovered by Henrietta Leavitt. The rate of their variability is related to how bright they actually get. And because of that, astronomers can use Cepheid variables to estimate distances, stellar distances. So it's one of the rungs of the distance ladder that they have. With Polaris, though, Polaris is not one that they use to measure distances because Polaris has a variable rate, and they're not quite sure what's going on there either. So just a little diagram. There's our Sun, and there's what Polaris would be sitting next to it. Again, it's an enormous star. That's Polaris A. So why has it not always been the North Star? Well, if you take a spinning top and you give it a little nudge, it'll do this wobble they call precession. If you give the spinning Earth a little nudge by gravity from the Sun or the Moon, it will also wobble and go through precession. So the Earth has the same kind of a wobble, so the north polar axis traces out a circle in space, which means it constantly points at different stars. It's about a 26,000 year cycle. So this would be looking northwest about this time of year. I chose this time because all the stars I was interested in were still above the horizon. So there's Polaris right there. Thuban, which was the North Star around 3000 BC, is right there. Alderaan, which will be the North Star 7500 AD. Vega, it'll be the North Star 14,000 AD. And this last one right above the horizon is Tau Herculis. So if you connect them with a circle, that shows you the amount of wobble that the Earth has across the sky. Notice that some of these, I tried to do this as accurately as possible. Some of these, the star is real close to the axis of rotation. Some they're pretty far away, like Vega won't get as close to the actual North Pole as Polaris is, and Polaris won't get as close as Thuban was. So we'll talk about those stars briefly. Thuban is an eclipsing binary. That is, it's two stars that are orbiting around a common center, and they're oriented in such a way that from our point of view, they cross in front of each other. It was the pole star when the Egyptians built the pyramids, and one of the theories they have is that the Egyptians waited to a certain time of night, and there's two stars that orbit that circle around Thuban that they call the indestructible stars because they never set. And they waited until these stars were lined up just right, and then used that to orient the north side of the pyramids. This one's about 300 light years away, and Thuban was more closely aligned with the North Pole than Polaris will ever be. So this is what the Egyptians would have seen looking north in the evening. Thuban is that dim little star right there. So that was the center rotation at the time. The two indestructible stars are Kokab and Mizar. They would circle around Thuban, so they wait till a certain time of night where they get this alignment and use that to orient the north side. Alderaan, it's the brightest star in Cepheus. It will be the pole star in 7500 AD. It's a white giant, 49 light years away. Rapidly spinning star though, it spins once every 12 hours, as opposed to our sun, which takes about a month to do a complete rotation. Vega, that's in Lyra. It will be the pole star in 14,000 AD. It's one of the three, if you come in the summertime, we always point out the summer triangle, and Vega is one of the three stars in the summer triangle. It's relatively close, 25 light years away, so it's the fifth brightest star in the sky. And if you ever saw it was an old science fiction movie called Contact. It was based on a Carl Sagan novel, starred Jodie Foster. Well, she supposedly received a radio signal that came from the direction of Vega. And the last one, Tau Herculis, is in the constellation Hercules. It's either a double or a multiple star, they're not real sure, about 300 light years away. And it will be the pole star, or was the pole star in 7400 BC. I'm always amazed at what some of these ancient scientists could accomplish. This idea of precession, the Earth's wobble, was first discovered by Hipparchus, who you see when he lived. He was a Greek mathematician and astronomer, and he took careful measurements of the positions of the stars and the position of the sun during the equinoxes, and compared that to much earlier records that he had access to, and realized that everything had shifted. But not only could he measure this, but he also was able to figure out why it happened. And it's just pretty amazing. So what does that mean for astronomy? Well, the problem with this wobble is that it makes celestial objects appear to shift position in space. So we have, if you want to locate objects on the Earth, you have our terrestrial coordinate system, latitude and longitude. Latitude's based on the equator as 0. Anything above it is positive. Anything below it is, or anything above it is north. Below it is south. And longitude is based on a line that runs through Greenwich, England. So you have east and west longitude. Well, we have a similar coordinate system for celestial objects called celestial coordinate system. And the easiest way to appreciate this is to imagine Earth as being inside a gigantic sphere. And all the celestial objects that we look at are on that outer sphere. So we can also put a coordinate system on that outer sphere. But what we use is, for baseline, we use a projection of Earth's equator out into space, and that becomes the basis for anything above and below. And rather than latitude, we call it declination. And we also, and for longitude, which is called right ascension, we use a point where the sun crosses the equator at a certain time of year. And that becomes the longitude 0, or the right ascension 0. But the problem is, as Earth precesses, it wobbles, or the projection of Earth's equator in space changes. And I'll show you that to you here. So say you want to look at an object now, and you look up the coordinates, and it tells you that it's right there. It's on the celestial equator. So it would have 0 degrees declination. 20 or 30 years later, you want to go back and look at that same object. And I'm going to exaggerate things here, but Earth is now wobbled some. Rotation axis has changed. The projection of Earth's equator in space has changed. So now if you go and look for something that's 0 degrees declination, your telescope would go here, but that object you were interested in is still up here. It hasn't moved. So the objects in space don't move, it's just the reference system that we use has moved. So what do? Well, they update the coordinates to all these objects about every 50 years. The current one we're using is called J2000. The previous one was 1950. But even 20 years later, if you put those coordinates into your computerized telescope, the 2000 coordinates into a computerized telescope and tell it to find that object, you'll probably still find it. It'll probably still be in your field of view. It won't be in the center, but it should be somewhere visible. So that's good enough for just casual observing. But if you need to do real science, then you need software which can update these coordinates in real time, and that's something that we can do here. So 2050, well, there may not be a 2050 set. The International Astronomical Union has agreed to change the coordinate system. Rather than using this variable reference system of Earth's equator, they're going to base the measurements on fixed objects in space, certain radio sources and certain stars. So that way the whole coordinate system won't change over human lifetimes. But we'll see. It's a controversial subject, and maybe they'll do it, and maybe they won't. So what about the rest of the planets? Do they have the same wobble to them? Well, there's scant information out there about the rest of the planets, but I was able to establish that everything except Mercury and Venus have the same kind of a wobble. In fact, Mars wobbles some 10 degrees, and that has caused some dramatic climate changes in Mars. Mercury and Venus, probably not. One of the prerequisites is that the planet has to be spinning fast enough that it becomes oblate. That is, it's wider at the equator than it is at the poles. And Mercury and Venus both rotate very slowly, and they're both almost spherical. So they probably do not precess. But all of the planets have an orbital precession. So you know they orbit around the sun in an elliptical orbit. Well, the long axis of that ellipse also rotates around the sun. And then just last thing here, this is not totally relevant, but I thought it was interesting. We already talked about this precession, Earth wobble. Earth also changes its obliquity, that is, its tilt to the orbit of the plane, to the orbit of the plane around the sun. So it tilts over a 40,000 year cycle, the tilt changes. And also the eccentricity of its orbit around the sun changes. It goes from being elliptical to almost circular and back again over a 100,000 year cycle. Each one of these cycles influences how much sunlight reaches the northern hemisphere, and which has most of the landmass. So some of these cycles increase the amount of sun that the Earth receives, and some decrease it. But every once in a while, over thousands of years, these cycles can line up just right and lead to prolonged periods of extremely warm temperatures, or they can line up just the other way and lead to long periods of extremely cold temperatures. So just to summarize, Polaris, our current pole star, easy to locate, not a particularly bright star, but it's easy to locate once you find the Big Dipper. And our precession wobble has led to different pole stars over the years. All of the planets have an orbital precession around the sun, and some of these various cycles can line up, leading to significant climate changes on our planet. They're known as Milankovitch cycles, after the geophysicists who first realized their relationship. Any questions? Joe, can you get the lights, please? Thank you.
Thank you,
All right, thank you for coming. Please come
Thank
again.
you.
Oh, one more announcement. If anybody's interested, we have an adult ed class starting next month. There's a little flyer on the whiteboard there that tells you a little bit about it if you're interested in signing up for it. It's through New Milford Adult Education. It's children friendly. Children can come to this as long as they have an adult with them. Okay, thank you very much.
Thank you.
Very good, Roger.
Thanks, Colin. So that's all you had to do was reboot the audio inserter?
That's what it looks like, yeah.
Okay.
Turn it off, just kind of wiggle the cables and
Yeah,
put it back on.
I don't know why it stopped to begin with, because like I said, it was registering when I first started, and then I didn't look at it after that.
Before we turn it down for a second, I'm trying to wiggle the cable back here and see if it just maybe, if it is loose,
Yeah.
probably see it cut out, sit back in it.
Yeah.
Time to replace it, find out why it's just doing that.
Glad you were here. I would have never paid any attention to it once it started.
There's still more people,
Okay.
if you don't mind.
No?
I'll do an announcement. What time is it now? Oh, good.
can't say it enough.
No autographs, please.
You're welcome.
On the sign. You feel like a student.
Right.
Really, really cool.
Jerry, you
thank
gotta
you.
come and volunteer.
I'm gonna come and volunteer. I'm working on it. I swear. I'm sorry. I'm
Good to see you too. Yeah, good to
Thank you. Really, really.
I know, it's so fun to see you. Take care.
I never knew Polaris was a multiple star system.
Yeah.
I learned something new. I didn't realize it was that large. So that's big enough. If that ever, at the end of its life, that'll probably supernova.
Yeah, I don't know. Good point. I don't know.
That's the
Very good, Roger.
Indian guy,
Thank you, John.
Chandra's Scar Limit, he said 8 solar masses are above supernovas.
I don't know what the math is.
So it'll look pretty big compared to the sun.
We were trying to learn
Hey,
that.
how are you? Nice to see you.
Yeah, it's not the best.
Well, the problem what we were having is kind of they give you these masks of supposed star fields that you're supposed to match up with what you have, and you couldn't see similarities at all.
So at some point, it's like,
Hello, how are you?
Fine, how are you?
I'm well, thank you.
in January, the database directory changed back to the C drive. That's probably why I stopped reporting, because it filled up the C drive again. I changed it to E, so for January from the 11th to the 21st, it was reporting here, and then it
When did we pull
switched
the
back.
drive?
You did it.
I know, I don't remember when that was.
It would have, it probably would have been that, that was not long after New Year's.
It was before the last presentation, because remember you came in and we couldn't get the audio to work for that one.
Yeah,
It was like a week before that then, so early January.
if I close this, reopen it. Things like that. Yeah, I did.
January 11th.
Yep, that would be consistent with this showing up here. 9:15 PM. Okay, I was reporting for tonight. Looks like it stays there.
Funny, I figured in the snow and such we'd have like maybe 10 people here tonight. Yeah, yeah.
Who was that?
A young lady in the first class.
Oh.
She remembers the presentation.
Oh my goodness. That's nice. Great. So you're going number 3?
Yeah.
And that's all I can gather.
Okay.
Yeah. Three all stars, but I was
I'll stay up, you stay up.
I didn't have a list almost. Are we ready? I guess that's it.
I'll get flights.
I got it.
Oh, I want everyone to know this adult ed is starting up again in March. It's a really fun course. It takes place right here, and it's family friendly. It's open to children as well as with adults. But it's a 6 weeks course starting in March, and just go through the for public recognize. That's how I got started here. It's a real fun class. So I just want everyone to know that. Thank you.
Good evening. Thank you for coming. My name is Roger Moore. The subject tonight is the real pole star. The title is supposed to be a little satirical. We're all somewhat familiar with the pole star, but when we ask people if they can find it, they often struggle trying to locate it or have misconceptions about how bright of a star it is. So we'll talk about that. Our pole star is not a single star, it's a star system, and it has some unusual characteristics, so we'll go into that a little bit. And the pole star that we have now has not always been the pole star, and it won't always be the pole star. So we'll talk about why that happens and implications it has for astronomy. So I'm talking, of course, about Polaris, which is in the constellation Ursa Minor, which is the Little Dipper you see in the center. The pole star Polaris is located right at the end of the handle of the Little Dipper. Unfortunately, we can't see most of the stars of the Little Dipper from our location, so we need a different way to find it. But it's visible all night on any clear night from northern latitudes. So if we had a clear night and you went outside and looked north, this is the view you would have. But why is it the northern pole star? Because it almost lines up exactly with Earth's north axis of rotation. Not quite, but almost. The name is derived from the Latin stella polaris, or pole star. And it's not one of the brightest stars. It's actually the 48th, or the 50th, depending on who you ask, brightest star. So this is a list of the 50th brightest stars. And I put this up here because several of these stars would be visible tonight if we had a clear sky. Sirius, which is the brightest star in the night sky, is up tonight. Pollux and Castor, which are both in Gemini, they're both up tonight. Rigel and Betelgeuse in Orion are both up tonight. Betelgeuse has become a very interesting star recently. It is, well, it always has been. It's a red supergiant, and it's a variable star. They know it varies in brightness over regular periods of time, but it doesn't vary enough that the casual observer would notice. But over the last 2 or 3 months, Betelgeuse has significantly dimmed. It's gotten dimmer than anybody around here has ever seen before, and they're not sure why that's happening. They're still trying to puzzle that out. But you have to go all the way down here to the bottom right of this list to find Polaris. So it's been used by sailors and explorers for navigation for centuries. And because it's at the north axis of rotation, if you can measure the angle to Polaris, well, that also equals your latitude above the equator. So the farther north you go, the higher Polaris appears in the sky until you get to the North Pole, and then it's straight overhead. And then the further south you go, the lower it is in the sky until you get to the equator, where you lose sight of Polaris. And unfortunately for the southern hemisphere, they don't have a corresponding South Pole star. The closest they have is a much dimmer star that's farther away from the axis of rotation. So how do you find it? Well, we're lucky because we have the Big Dipper, and everybody can recognize the Big Dipper. So if you simply go to the far end of the bowl of the Big Dipper and follow these 2 stars, well, they point right at Polaris. Just follow that direction till you get to the next brightest star. And the beauty of doing that is it doesn't matter which direction the Big Dipper is facing, it still works. You start at the bottom of the bowl, Follow these two stars out, and it'll still point you to Polaris. So once you know Polaris, then you know all 4 different compass directions. You can also use it to get a rough idea of your latitude above the equator. So an adult's fist held out at arm's length covers about 10 degrees of the sky. So you put one fist on the bottom of it on the horizon, and you just stack them like this until you get to Polaris, which works out to be about 4 and change from our latitude, which is about 41.5 degrees north. If you could go outside and face north and watch the sky for 24 hours, I'll show you a little animated video of what you see. As you watch this, pay attention to what happens to Polaris, and then also watch what happens to the Big Dipper. So notice Polaris doesn't appear to move at all. And the Big Dipper always stays above the horizon. So it's always there to help you find where Polaris is. And also because of this, you can do, anyone with a digital camera and a tripod can do cool things like this. You point your camera at Polaris and just take a series of long exposures. This was 90-second exposures. And then stack them together in software, and you can see for yourself how Earth rotates. So Polaris is about a 70 million year old triple star system. Polaris A is the one you see in the sky. Polaris B, most small telescopes can pick out Polaris B, but Polaris B was discovered by William Herschel in the late 1700s. Even back in 1930, they knew Polaris A had a close companion because the star wobbles across the sky. But it wasn't until about 2006 that the Hubble telescope was actually able to image Polaris AB, its close-in companion. So Polaris AB is about 3 billion kilometers away from Polaris A. Big number, is hard to get your head around, but when Earth and Pluto are both on the same side of the Sun, they're about 3 billion kilometers apart. So it's about the same distance as Earth to Pluto. So it's not a remarkable star in our skies, but it is actually an enormous and very bright star. It's what's called a yellow supergiant. It would be 2,500 times brighter and about 45 times wider than our Sun. But it's far away. It's almost 480 light years away. And it is the closest Cepheid variable. Cepheid variables are stars that pulsate in brightness. They vary over a regular time frame. And they are one of the stars that astronomers use for measuring celestial distances. And it was Henrietta Leavitt who established this relationship in the early 1900s, that with Cepheid variables, if you measure the rate that they vary, it'll tell you how bright the star actually gets. And astronomers can use this to measure celestial distances. But with Polaris, they don't use that. They don't use Polaris as a Cepheid variable because the rate of brightness of Polaris has been changing. It varies over the years. So a little diagram, there's our Sun, and there's Polaris, if they were next to each other. So why has Polaris not always been the North Star? Well, if you take a spinning top and you give it a little nudge, it'll start this wobble known as precession. Well, Earth gets a little gravity nudge from the Sun and the Moon, and it also precesses. It also wobbles. So the rotation axis traces out a circle in space. So it's always pointing at different stars. But this circle takes about 26,000 years to be completed. But if you look, this was looking northwest end of January. I chose this time because all the stars I was interested in were still above the horizon. So we can all find Polaris now, right? There's Polaris. There's Thuban, which was the pole star in 3000, roughly 3000 BC. Alderaan will be the pole star in 7500 AD. Vega, if you come here in the summertime, we almost always point out Vega. It's one of the stars of the summer triangle. Will be the pole star in 14,000. and Tau Herculis was the pole star in 7400 BC. I give you one date that these are the pole star, but remember this is a repeating cycle. So if you draw a circle around that, that gives you an idea of roughly the amount of space that Earth rotation wobble covers. So we'll talk about each one of these briefly. Thuban is an eclipsing binary. That is, it's two stars that are orbiting around a common center, and from our line of sight, they actually cross in front of each other. It's the pole star when the pyramids were built. And one of the theories they have is that there are two stars that circle around Thuban as the Earth rotates. And the theory is that they waited until these two stars, which they called indestructible stars, lined up. They call them indestructible because they never set. So they waited until these stars lined up just right, and then they used that to orient the north side of the pyramids. So it is a blue-white giant star, 350 times more luminous than our sun, and about 300 light years away. And it was more closely aligned with the North Celestial Pole, or the North Pole, than Polaris will ever be. Polaris is close, but it's not exactly on the axis of rotation. So this is what the Egyptians would have seen. This is going back to, I put 2787 BC in here. This is what they would have seen looking north. So their pole star was Thuban. If I showed you a video of this time, everything would rotate around Thuban. And the two indestructible stars they used were Kokab, which is in the Little Dipper, and Mizar, which is in the crook of the handle of the Big Dipper. So those two stars would appear to be circling around Thuban all night. And if you wait till just the right time when they're lined up like this, then you can use that to orient the pyramids. So that's one theory. One thing I learned while researching this is there's still a whole lot they don't understand about how the pyramids were made. Next one, Alderamin, it's the brightest star in Cepheus. It'll be the pole star in 7500 AD. And it's a white giant star, but it's rapidly spinning. It spins about once every 12 hours, as opposed to our sun that takes about a month to go through a full revolution. Vega, again, if you're here in the summertime, Vega is, we always point that out. It's in the constellation Lyra, the pole star in 14,000 AD, and it's only 25 light years away, so it's a relatively bright star. It's our fifth brightest star. It's also a blue-white, rapidly spinning star. And if anybody saw it, it was an old science fiction movie called Contact, based on a Carl Sagan novel. She was supposed to have received the signal, radio signal, came from the direction of Vega. And the last one, Tau Herculis, which is in Hercules. And it's either a double or a multiple star system. They're still not sure. About 300 light years distance, and it was the pole star about 7400 BC. I'm frequently amazed at the science that some of these ancient astronomers could accomplish. This was Hipparchus, who lived, you see when the dates that he lived, Greek mathematician, and he took careful measurements of where the stars were in the sky and where the sun rose and set during the equinoxes, and compared that to more ancient records he had, and realized that things had shifted. But not only could he make that measurement, but he put it all together and figured out what was happening. It's just amazing. So what does that mean for astronomy? Well, on Earth we have a terrestrial coordinate system. If you want to find something on Earth, you have latitude and longitude. Latitude is based on the equator. Anything above it is north latitude. Anything below is south latitude. Longitude is based on a line running through Greenwich, England. So you have east and west longitude. Well, we have a similar system for celestial objects that we call the celestial coordinate system. And the easiest way to picture this is to think of the Earth being inside a giant sphere. And all the celestial objects are on that outer sphere. So then you can take and paste a coordinate system onto that outer sphere also and use that to find celestial objects. So we use the projection of Earth's equator out into space as the 0 degrees latitude, which is actually called declination. And then we use a point where the sun crosses that line at a certain time of year, and that becomes the 0 point for longitude, or what's called right ascension. But the problem is, as Earth wobbles, the projection of Earth's equator out into space changes. So I'll show you kind of a diagram here. I'm going to exaggerate this a little bit, but so let's say you wanted to find an object, and it was located right there on the celestial equator, and you look up the coordinates, it tells you it's 0 degrees declination. It's not above or below, it's right on the celestial equator. But several years later, you want to go back and look at it again, and I'll exaggerate things here a little bit, but now Earth has wobbled, its spin axis has changed direction, its equator has changed. So now if you go and look up coordinates to something and it tells you it's at 0 degrees declination, you'll look right there, but the object you were looking at is still there, it hasn't moved. So what they do is they update these coordinates every 50 years. The one we have now is called J2000. The previous was in 1950. But even several years later, if you take the J2000 coordinates and plug them into your computerized telescope, it'll still find the object. It might not be centered, but it should be within your field of view. So that's good enough for observations. But if you need to do real science, that's not close enough. You need to have software that updates these coordinates in real time, and that's what we have here. And you know, I think the next one might be 2050. Well, maybe not, because the International Astronomical Union has agreed to change the reference system, and they may base it rather on a projection of Earth's equator out into space. They may change the reference system to reference a fixed set of sources in space, a fixed set of radio sources, a fixed set of stars, so that way the coordinate system won't change over time as it does now. But we'll see. It's a controversial subject, and maybe they won't change it at all. So do the other planets have an axial precession? Well, there's little information out there about the rest of the planets, but I was able to find that all the rest except Mercury and Venus also go through the same wobble that we have. In fact, Mars wobbles some 10 degrees every 120,000 years, and that has caused some dramatic climate changes on Mars. Mercury and Venus, probably not. One of the prerequisites for this wobble is that the planet has to be spinning fast enough to become oblate in shape, that is wider at the equator than it is at the poles. And both Mercury and Venus rotate very slowly, and they're both nearly spherical. But all of the planets also have an orbital precession. As you know, the planets orbit around the sun in an elliptical fashion, and the long axis, well, the long axis, the short axis of that ellipse also rotates around the sun. And then finally, this last slide is not terribly related, but I thought it was interesting. So we talked about this precession that Earth goes through. Earth also has an obliquity, that is a tilt to the plane of its orbit around the sun. And that obliquity changes through a 40,000-year cycle. And it also changes the eccentricity of its orbit. That is, it's sometimes fairly elliptical, and sometimes it's fairly circular. And each one of these cycles influences how much sunlight is exposed to the northern hemisphere, which has most of the land mass. So some of the cycles increase the amount of sun's exposure, some of them decrease the amount of sun's exposure. And over long periods of time, thousands of years, some of these cycles can line up and lead to prolonged periods of extremely high temperatures on our planet, or just the opposite. They can line up and lead to long periods of extremely cold temperatures. Fortunately, we're in a mild phase right now, and we will be for a very long time. So just to summarize, our Polaris, our current pole star, is not a terribly bright star, but it is easy to locate using pointer stars in the Big Dipper. And Earth's precession has led to different pole stars over thousands of years. All of the planets have an orbital precession around the sun, and that's also due to gravitational interactions between the planets. And then some of those cycles that the Earth goes through can line up, leading to extreme climate changes that are called Milankovitch cycles, after the geophysicists who first put that all together. Any questions?
When we're seeing the Polaris, are we actually seeing the
the singular one, or its neighbor, the one you said was actually?
No, but the question is, when we look at Polaris, are we seeing the singular one? We are seeing Polaris A,
Right.
the larger one.
Okay.
It takes even a small telescope for you to see Polaris B.
Mhm.
It's farther away companion, but we see Polaris A with our own eyes.
Okay. Thank you.
But it's not binary, they're too far away, A and B.
It's a trinary.
It's a triangle.
It's a trinary. Polaris B also is part of the system. So Polaris AB, the teeny tiny one's real close, is orbiting around Polaris, as is Polaris B. It's a triple star system. I thank you. Thank you for coming on this crummy night.
Was the lights all right?
Please. Thank you.
That was good, Roger.
Thank you, Elaine. Yeah, cool.
I learned that, it was a multiple star system. Well, just one star.
All right, we're ready for the fourth show.
What? We're ready for the
He's
first
the
one.
YouTube.
You have to watch it in reruns.
Show, I missed the first three.
Oh, okay.
Hey, all right. Good.
Just, like you're talking about Polaris being like a three-star system, so would they be, if there was a solar system around them, so they would be in the center, or
Should have mailed it to
kind
you.
of revolving around each other, and then the planets would be around them? How would that
They
work?
have found planets orbiting double stars, and
We got it
if I remember right, they found it both ways. They found a planet that orbits around both of the stars, and they also found a planet that orbits around one and not the other. So it could be.
Who knows?
Yeah, who
Yeah,
knows, yeah.
right.
It works really well.
Yeah,
Good. I mean, it's impressive to
that's
see what
really,
you do.
yeah, that's pretty
That
neat.
one boggles the mind.
Yes, it does, it does. It does.